Okay, girls, so today I just want to talk about Born-Haber cycles. So far we've looked at Hess's cycles, where when we're going with our reactants to our products, we've said that if we need to, we can go via an alternative route and we can look at a different reaction, and that the overall enthalpy change for this reaction is going to be equal to the overall enthalpy change for the other reactions. So my enthalpy change for reaction 1 is going to be equal to my enthalpy change for reaction 2 and the reverse of my enthalpy change for reaction 3. Okay. Now, Born-Haber cycles that we're going to be looking at today are a similar process, okay, but these are multi-step processes. So if I was looking at the reaction to form sodium chloride, okay, we have sodium metal reacting with chlorine gas, half a mole of chlorine gas, to form sodium chloride. And while this equation tells us that the reaction happens, it doesn't exactly tell us what is happening at an atomic level. And this is where a Born-Haber cycle comes in. So we're going to start off at the bottom of the page. Okay, so you always need lots of room for a Born-Haber cycle. We're going to start off our reactants. Okay, so I've got my sodium metal, I've got my chlorine gas. We put the elements in their state at room temperature. And then below them, because we know that this is an exothermic process, we're going to have our product that we're looking for. Okay, and in this case, it's sodium chloride solid. And this is the enthalpy change that we're looking for. So my enthalpy of formation that we're going to calculate. Now, for atoms to react, they need to be in the gaseous state. Okay, so the first thing I'm going to do is I'm going to convert my sodium from sodium metal into a gas, and this is called the enthalpy change of atomization. Okay, so I'm turning my metal into an atom, and for this value for sodium, it is 109 kilojoules per mole, and we can get this value from a data booklet. The next thing I need to do is I actually need to convert my sodium atoms into sodium ions, because sodium chloride is an ionic substance. So I'm going to remove one electron from my sodium, and this is my first ionization energy for sodium, and I can look at this up in the data booklets, and this takes 496 kilojoules of energy to complete to occur. Again, it's an endothermic process because energy is going into the system. Now I need to go and look at my chlorine. So I've got my sodium ions, but they need to react with chlorine ions. So the first step is to go from chlorine molecules to chlorine atoms. Okay, so I'm going to go to a mole of chlorine gas, and this is my enthalpy of atomization of chlorine. Now, since I'm breaking half a mole of chlorine, this is half my bond enthalpy, so this is going to be 121 kilojoules per mole. All right. Now that I've got my chlorine, I need to turn it into chloride ions, and so this is my electron affinity for chlorine, and this has a value of minus 349. So now I'm going down the way because I'm looking at exothermic processes. So now I have sodium ions and I have chloride ions, and these are both in the gaseous stage. Now, once I have both my gaseous ions, I can then react them together to form my solid lattice, and this is my lattice enthalpy of sodium chloride. And again, this value is in your data booklets, and for that it's minus 790. So to calculate my enthalpy of formation, I'm just going to add together all my values. So 109 plus 496 plus 121, and then minus 349 minus 790, and this is going to give me my overall enthalpy change for my reaction and my enthalpy of formation of sodium chloride.